Well, good evening, ladies and gentlemen, from all over Ireland, which is great to see, and welcome to Astronomy Ireland's March lecture. I'm David Moore, chairman of the club and editor of the magazine, and we're very delighted this evening to welcome Laura Murphy, who's going to talk about the first stars in the universe. Very exciting topic that we've all been looking forward to. We're still admitting a few people, so I'll just tell you a few things about the club before we continue, especially those of you who are new and haven't been with us before. Our format evening will be a little bit about what's been happening in the past in astronomy in Ireland, then of course the present, which is our main talk of the evening. You get a chance to ask questions at the end, and then a bit about what's some events that are coming up in the future, including a very brief look at what's happening in the sky. And there are some really fascinating things for you to see over the next 4 weeks before our next talk in April, which we'll tell you about at the very end, the April talk, that is. So as I said, it's great to see people from all around the 32 counties joining us. I think we even have 1 or 2 international listeners or viewers. So you're all very welcome. It's great to be able to do this at last. I remember 30 years ago when we formed Astronomy Ireland, we wondered, should we just be a local Dublin-based society or take the more difficult option, which was to become a national organisation? And to be fair to the whole committee, they all wanted to be a national organisation, and Zoom has allowed us to do this. So it's the only silver lining to this cloud we're all under at the moment. As I said, we celebrate our 30th anniversary last year, or at least we were trying to celebrate it. We celebrated with a few words, but we're still hoping to have our big annual barbecue event, which is our big annual fundraiser every September or so, set for September the 4th this year. Hopefully, we'll be able to see you all in person by then. That'll also be our 30th anniversary celebrations. Our anniversary ran from August 1st last year until July 31st this year. We might extend that a little bit under the current circumstances. The talks are free, but you're welcome to make a donation. At any stage, you can go to astronomy.ie/donate now or in the future and help us to run the society. We're a non-profit run by mostly volunteers. We are the world's most popular astronomy society now, with more people per head of population in this country than anywhere else in the world, which is fantastic to see, and we want to keep that going. The only advantage that lockdowns have had is that people are turning back to their hobbies, including astronomy, and Astronomy Ireland's membership has doubled in the last 12 months. So we are doing extremely well, and we want to keep that up and keep you all entertained so you stay with us for the next 30 years. So what do? Well, we have these monthly talks now online. You can actually get back talks on DVD. Some of them will be on YouTube for a while and also available online on the Zoom platform as well. But if you go to astronomy.ie/DVD, you'll see lectures going back over a decade by all kinds of people, from the Astronomer Royal of Scotland to Professor Brian Cox and lots more besides, in all aspects of space and astronomy. We also run evening classes twice a year, usually January, February, and then in October. I think our October class is starting on October the 12th, and our current classes are coming to an end. They run for 8 weeknights, about 2 hours long with a break in the middle. And they're aimed at beginners to bring you up to a level where you'll understand everything in the magazine. But don't worry, you don't have to understand everything in the magazine. The magazine is aimed at the general public. It'll be posted to you if you join as a member every month, usually a week or 2 before the month begins, so you know what's coming up in the sky for the following month. But we also report on what people are seeing from all around Ireland and all the big international stories. Lots of news about Mars and landers at the moment, for instance. But we also have an Irish angle on each of those stories. There's usually somebody like Laura, who's an expert in a particular field in a research institute in Ireland, that we can get to give a comment on the overall picture. So we pride ourselves as being a very competent magazine. We've been doing it for 30 years, so I hope by now we've learned how to do it right, and that we enthrall you with the magazine every month, and you'll keep your subscription up for the next 30 years, as I said earlier. And we also used to do talks in schools. We've done a few online since the lockdown. The schools not being in, it's been quite difficult. We used to reach tens of thousands of students every year. We missed that, but hopefully that'll all be back online, certainly by the end of this year. We also maintain a huge media presence, sending out lots of notices to about 1,000 journalists around the country to try and keep astronomy in the mainstream. And we've been helped on that by what's been happening since our last talk by all the Mars landers. In fact, our last talk was the exploration of the gas giant planets by Dr. Katrina Jackman, who's now from the Dublin Institute for Advanced Studies, but was working in Imperial College London and UCL in London on the Cassini mission, that fantastic spacecraft that orbited Saturn for all those years and sent back amazing results, which she showed us, along with plans for future exploration as well. As I said, if you missed that talk, you can still get it on DVD. Go to the website and have a look. I'm quite aware that our last speaker was female, and our New Year lecture, which was our January talk, was also given by two ladies. And tonight's talk is another female speaker on International Women's Day, which I think is a perfect example of how women certainly are making fantastic advances in astronomy, and long may it continue. We don't think we planned that deliberately, but it's nice to see it all came together in such a nice way. So let me tell you a little bit about what we've been doing since the last lecture. Lots of radio interviews about the Mars Perseverance rover, but the media are focusing on that. Don't forget the Chinese landed the week before. Well, so they didn't land, arrived at Mars. They're going to land in a few months when they've checked out their orbiter and its lander. It's no mean feat to land a spacecraft on Mars, so we wish them all the best with that. We have an excellent writer in our magazine, Brian Harvey, who's written a book, an international book on the Chinese space program. So he has lots of great contacts in China, and they're very cagey about the material that they release, unlike NASA, who are always looking for publicity and have a fantastic public affairs office. So we'll be able to get you the inside scoop on the Chinese orbiter and lander. And then the Arab nations landed as well the day before the Chinese they didn't land, they arrived at Mars with their own Mars probe that's going to map the atmosphere and the climate of Mars as well. And for a relatively small nation to put together such an impressive mission and be successful is another major story. And you'll read all about those in the next issue and indeed subsequent issues of the magazine. So I won't tell you more about them now. We did lots of other radio interviews as well. We had a major fireball, which is thought might have dropped meteorites onto the Britain mainland, probably between the border of Wales and England, somewhere around that area. You'll be reading about that in the magazine. That generated lots of publicity. And of course, in the skies, we've had the International Space Station flying over every morning. We had a space chase at one stage. I actually saw it myself. And now, just last week, another tranche of these Starlink satellites, which really are vermin of the sky, unless they can find a way to dim them down, they don't ruin all the research that goes on in the sky, as they put up this broadband constellation of Starlink satellites. But they do look pretty in the sky, it has to be admitted. And I saw them the other morning, 60 of them following each other very closely together. A very impressive sight. They're spreading apart slowly as each day goes by. The first week or so is always the best time to see them really close together. And other people have reported seeing them as well. So watch out for them tonight. And if you want predictions of the Starlink satellites and the International Space Station, join us on our social media, which is free. So if you go to our website, astronomy.ie, go to the homepage, you'll see there's Facebook and Twitter symbols there. Click on those, and that's where the predictions will be posted every afternoon for that night and the following morning. So for instance, I'll give you a sneak preview. At 5:32 a.m., those 60 Starlink satellites cross very high over Ireland. They'll be really easy to see if it's clear. And the International Space Station flies over at the same time as well, which is a remarkable and an unusual treat. So do set your alarm for just before 5:30. Hopefully you'll get a break in the clouds and you'll get to see those. If not, we'll have the prediction for the following day and each subsequent day for the next few weeks for the Starlinks and the International Space Station. And although it's a question of getting up at dawn at the moment, the International Space Station will move into evening skies later this month. So it'll be much easier to see it. And we'll keep you posted on that as they launch more and more of these Starlinks. So that's a bit about what's been going on. Hopefully everybody's joined us now. We can start the main business of the evening. We're delighted to welcome Laura Murphy, who's a PhD student in the School of Physics at Trinity College, where she's studying the first stellar explosions and their progenitors. She was awarded an Irish Research Council Postgraduate Award in 2017 to fund her research. And she's also a member of the Supernovae and Stellar Evolution Research Group led by Professor Jose Groh, who actually gave a talk to Astronomy Ireland, I think it's about 2 years ago now, more on Supernovae if you want to check that out on the website as well. Her own work aims to understand the nature of the first stars and their explosive deaths as supernova, because the early universe was a crazy place, and I'm keen to find out a lot more about it. The James Webb Space Telescope is going to help us when it's hopefully launched in October this year, and I just can't wait. So without any further ado, I'm delighted to welcome Laura Murphy to talk about the first stars in the universe. Over to you, Laura.
Thanks so much. I'll just share my screen. So yeah, thank you for that lovely introduction. So as was said, my name is Laura Murphy and I'm a PhD student in the Massive Stars and Supernovae group in Trinity College Dublin, led by Professor Jose Groh. So I want to say again, thank you so much to Astronomy Ireland for inviting me to speak with you today. I'm delighted to get to share some of my research with you. So I will be talking about first light, the first stars in the universe. Before I do so, I just wanted to wish everyone a happy International Women's Day, as has already been mentioned. The theme this year is Choose to Challenge. So that's to challenge our inherent gender bias and challenge any gender inequality wherever we see it. And I suppose just given the day that's in it, I wanted to raise some or share some organizations with you that are working towards gender equality in science. So there are plenty now that you could mention, but here are 4. So feel free to check some of those out and see if there's any way in which you could support them or perhaps get involved. They do great work. So anyway, moving on to the talk itself. So I usually start the public talk by asking, first of all, what is a star? So there are many answers that I've gotten to this question, but really it all boils down to a star is just an enormous ball of gas that's held together by its own gravity. The structure of the star is a little bit more complex though. So really it's made up of the stellar core, and this is where most of the nuclear burning reactions will happen, which is surrounded by an envelope of material. And as I said, this is all held together in this spherical shape by the star's gravity, because stars are so massive that they have their own gravitational pull, which holds them together in this way. But then why don't they just collapse inwards? Well, that's because they're generating lots of pressure from all of the nuclear reactions that are happening within the core. So how does it shine? Well, it shines through these reactions. So a star will begin its life and it will be made mainly of hydrogen. And when the star starts its life, that happens when it can burn hydrogen in the core, or when it can fuse hydrogen in its core. So the first stage and the longest stage of a star's life is what we call the main sequence, and this is when you have hydrogen fusion in the core. So how does that work? You're essentially smashing 2 hydrogen atoms together to produce helium. And when you do so, you produce lots and lots of energy. In fact, there's a lot of research going on at the moment into building hydrogen fusion reactors on Earth, because this would be a really efficient energy source for us. And that's how stars are powered throughout their lives, is through these fusion reactions. So this will continue happening until you run out of hydrogen in the star. And at that point, now you have a core that's made mainly of helium. Now the core is really hot. The core had to be roughly 10 million degrees in order to fuse hydrogen, so very, very hot. But in order to keep burning fuel, it needs to be even hotter, because if it's going to have helium fusion, it needs to reach temperatures of roughly 100 million degrees. And it does so by contracting. So that star contracts until the core is hot enough, and then we have helium fusion. And so helium fusion will then continue then producing heavier elements until you run out of helium, at which point, if the core can be hot enough, you'll have carbon fusion, and then onto neon fusion, and so on, until you end up with an iron core. And what's special about the iron core is that in order to fuse iron, it would now take more energy than it would produce. So this is what we call an endothermic reaction, if you remember that from your chemistry in school. At this point now, the star has no way of producing any more energy for itself. So what happens? Well, now we don't have the pressure coming outwards from the core. So the core can no longer balance that gravity. And so the star compresses and compresses until eventually there's so much pressure on the core that you get an explosion. And this is where we get a supernova. So it's from all of that pressure, the core compressing, and then you get this explosion. And what happens then is the outer layers of the star are ejected into space. And so this is how we enrich the universe with heavier elements. So all of the heavy elements in the universe, all the carbon in your body, it's very likely that that came from a supernova explosion a long time ago. So it's very important to understand these explosive events because they tell us about the history of the universe and where all of our elements come from. But that said, not all stars explode. It actually depends on the size of the star or the mass of the star. So when I say the mass of the star, I might use this symbol, and we give the mass of the star in terms of what we call solar masses, which is the mass of the sun. So the sun is 2 by 10 to the 30 kilograms. So that's a 2 and a lot of zeros. So it's very, very massive, but there are in fact plenty of stars in the universe that are larger than our sun. And to describe how massive they are, we use this solar mass. So if I was to say that the mass of a star was 8 solar masses, I would be saying that it's 8 times bigger than the sun. So let's explore the final fates for stars of different initial masses. So first of all, we'll look at the lower initial mass case of stars that are less than 8 times the size of the sun. So we would expect these objects to end their lives as white dwarfs. A particularly famous example of a white dwarf is Sirius B. Now you may have heard of Sirius A. So Sirius A is the brightest star in our night sky. It's twice the size of our sun. And for a long time, it was thought that Sirius A was a single star. But then it was discovered that there was this faint dot here, which is Sirius B. And so in fact, this was actually and is a binary system. So what I mean by a binary system is 2 stars that are rotating around each other. And if those stars are close enough to each other, then they'll actually be able to interact and maybe even exchange some mass between them. And when that happens, if one star, Sirius A in this case, is able to gain a lot of mass from Sirius B, then it gets itself more fuel so it can live longer. And so that's why Sirius A is bright and shining, and Sirius B is now this fainter white dwarf having ended its life. And the reason they don't explode is essentially that their cores can never get hot enough to burn through all of the material and produce an iron core. So that's why we end up with this sort of faint, it's essentially the core of the star left over. It's all made up of carbon and oxygen and it's very dense. But that's how these stars are expected to end their lives. So moving up in mass then, between 8 times the size of the sun and 40 times the size of the sun, this is where we start to see supernovae. And when you have a supernova explosion and all of the envelope is ejected into space, that leaves the core, and the core ends up as either a neutron star or a black hole, depending on the mass of that core. So a famous example that we have of a neutron star is here in the Crab Nebula. So the Crab Nebula is the remnants of a supernova that happened roughly 900 years ago and was observed here on Earth. And this amazing image really is from the Hubble Space Telescope. So it's this zoom in of the Crab Nebula here, and you can actually see the neutron star here at the center. And this is pretty special to see the neutron star at the center of that remnant, because there's all of this mass around it, and you can actually see all of the mass spinning around it here, because a neutron star is essentially a very dense, highly magnetized and rapidly rotating, rapidly spinning star. So it's very energetic. So this is all the material whipping around it here that you can see in the image. So that's what you would expect to see up to an initial mass of 40 times the size of the sun. If we move on up then, now up until roughly 140 times the size of the sun, we'd expect for the star to directly collapse to a black hole at the end of its life. And I can't talk about black holes without mentioning this wonderful image here, the first direct image of a black hole from the Event Horizon Telescope. And this is really amazing because it's so similar to what our models have predicted. You can see the black hole here, the event horizon, where light can no longer escape from. And this is the accretion disk. This bright ring is the accretion disk around the black hole, where material is sort of being eaten by that black hole. It's being sucked in by its gravity. So that's a very exciting image. Moving up then in mass again, so up to 260 times the size of the sun now. This is where we expect to see pair instability supernovae. Now, don't worry too much about the name. It's just a really big supernova. And these are special because they leave behind no remnant. So what that means is that the explosion is so strong that the entire core is exploded. And so this is very important for enriching the universe with really heavy elements like iron. So it's important for us to know how many of these there were in the early universe, for example, if we want to understand how quickly the universe was enriched with these heavy elements, which could have been used to make planets, etc. And then finally, the most massive stars that we know of then, again, would be expected to directly collapse to a black hole. So this region here, where we go from black hole to no remnants left behind to black holes again, this is what's known as the mass gap in the astrophysics community. And this is a highly debated topic. But there's a lot of work being done at the moment to understand the masses of black holes and what we would expect to see in the universe. And you might have heard of the LIGO collaboration. So this is the facility that is observing the universe through gravitational waves. So this is very exciting. And the blue dots here are all of the black holes, all the masses of the black holes that have been detected using gravitational waves. So this is a really exciting, completely new way for us to study the universe. It's the only way that we can study the universe without relying on light. So it's very exciting for seeing very far away. So moving on now to the first stars. So now that you understand the kind of general overview of the lives and deaths of stars, let's talk about how the first stars were different. So to ask what's different about the first stars, I'm going to compare them to what I'll call solar-like stars. So this is just stars of the same initial composition as our sun. So our sun would have started its life with 72% hydrogen, 26% helium, and about 2% of heavier elements. So those heavier elements would have come from the explosions of massive stars a long time ago. And the first stars, however, didn't have those heavier elements because they were the first stars. So they actually had what we call a Big Bang composition, because the only elements available to them were those that were produced in the Big Bang. So they would have been made up of roughly 75% hydrogen and 25% helium when they started their lives. Another key difference between them is the typical masses of the stars. So in our galaxy, in the Milky Way, in the modern universe, stars of greater than 10 solar masses are very rare. So most stars would be more along the size of the sun or even smaller. Whereas in the early universe, we would expect that a typical mass for the first stars would be 20 to 40 solar masses, on the order of tens of solar masses anyway. And this is to do with the fact that the environments that they formed in were much hotter. So we would expect to have much more massive stars then. Some other key differences: solar-like stars lose a significant amount of mass through stellar winds. So you might have heard of the solar wind. So this is the constant mass loss from our sun. So all the time we have all of these charged particles coming at us from the sun. And there's a lot of research into this because we need to understand the solar wind really well in order to make sure that our satellites won't be broken, and to keep an eye out for solar flares, as they're called. So this is if you get a big bubble up and you get lots of charged particles coming at us at once, and we need to be really mindful of that now that we rely so heavily on our satellites. But all stars of a metallicity or a composition similar to the sun would have a wind like that. And it's actually driven by those heavier elements like iron at the surface. But the first stars didn't have those heavier elements at the surface, so they wouldn't have lost mass, at least not through a wind in this way. The first stars are also expected to be fast rotators, so to have spun much quicker than stars like our sun, and they're also expected to be hotter and more compact. So how does this affect their evolution? Well, because they're more massive, then we expect to see more supernovae, more neutron stars, more black holes. So these are some artistic impressions now of what a supernova, I should say, looks like. A neutron star, so if you remember, I said it was highly magnetized. This would be all of the magnetic fields. And this is the artistic impression of the black hole, which is based on models that have been run. And again, it's really amazing how similar our models were to when we finally got that direct image. So that's really amazing. But yeah, all of these events are very important for shaping the universe. So understanding how many of them would have been produced by the first stars is very important. And we do expect the first stars to have been much more massive than typical stars today. So we would have expected to see a lot of these. Because the first stars had less heavy elements, as I said, they'd be more compact and they'd be hotter, so they spin up more easily. So what I mean by spin up is, if you think of the typical example is the ice skater, and if they're spinning with their arms out and then they pull their arms in, then they'll spin a lot quicker. So if a star is more compact, it will spin up a lot more easily than a star that, say, has a larger radius for the same initial mass. They're hotter, so it's easier for them to start a new nuclear burning phase in the core. So if you remember, I said that to have hydrogen fusion, the core has to be 10 million degrees, but to then burn helium after that, it has to reach a temperature of 100 million degrees. So in stars of a solar-like composition, the core might have to contract quite a lot in order to start the helium burning phase. But for the first stars, because they're hotter, it's much easier to start that new phase. They're also expected to have higher rotation, to spin quicker. So that means that they would have more mixing, they'd be able to mix more fuel into their core, so they'd have longer lifetimes, and they'd also have more heavy element production then. So why are the first stars important? So the first stars are very important because they're the ancestors of all stars. So they tell us a huge amount about the history of the universe. So this picture here shows us the evolution of the universe from the Big Bang to modern day. So we have the Big Bang and the beginning of the universe. After the Big Bang, it was all fully ionized. And then after more expansion, as the universe cooled down, then all of that material cooled and you formed neutral hydrogen. And then the first stars formed. So the first stars formed, they reionized that material, they chemically enriched the universe, and they shaped all of the galaxies that followed. So if we want to understand how the universe got to look the way it is today, then we need to understand what the first stars were like, because that's what's going to tell us about how the universe came to be the way it is. So can we see them though? Well, soon we will be able to see the first stars. Maybe not the individual stars, but we'll be able to see a cluster or a population of these first stars, and we'll be able to see their explosions. So this is very exciting. We'll be able to do this with the James Webb Space Telescope, which, as was said at the beginning, is set to launch in October 2021. So this will be a very exciting new era in astrophysics research for us, and we'll have observations way back to when the first stars were in existence. So you might be asking, but how? Because as I said there, this will allow us to see back to when the first stars were in existence, because you have to remember that the first stars would have formed and lived roughly 13 billion years ago. So that's a very long time ago. And unless they're very, very small, and we expect most of them to be quite massive, that would then mean that they're now dead. So how do we see them then? Well, we have to see back in time. And that sounds kind of sci-fi-ish, but actually we can see back in time because light travels at a fixed speed. So to us on Earth, it seems that light is instantaneous, but actually, if you were very, very far away, it would take light some time to get to you, and space is very, very big. So actually, a unit of distance that we use in space is a light year, and 1 light year is just how far light can travel in 1 year. So if we take the example of the sun is 8 light minutes away. So if you were to look at the surface of the sun, then what you would be seeing is actually from 8 minutes ago, because it takes the light traveling from the surface of the sun 8 minutes to get to us. Similarly, if you take the next nearest star to us after the sun, that's 4 light years away. So if you're to look at that, you would be seeing that star 4 years ago, because it takes the light 4 years to travel from that star to us. And the same can be true if you're talking 13 billion light years away. That's very, very far. But if you can see back that far, then you're actually seeing 13 billion years ago. So we just need really strong and really good telescopes. So this image here shows how far back in time the Hubble Space Telescope can see, and the James Webb Space Telescope is going to extend that back into the era of the first galaxies. So this is a very exciting time to be working in studying the first stars, because soon we'll have a lot of answers to the questions that we've been asking for decades. As I said, soon we're going to have some very exciting observations, but we need to have models in order to understand those observations. When we see those first populations, we want to understand how the first stars would have evolved so that we can understand what it is that we're seeing. So that's where we come in. How we study the first stars is through stellar evolution modeling. So what do I mean by stellar evolution modeling? Well, really, we're just creating a sort of a fake star in a computer. And we do so by starting with an initial mass, an initial composition, and an initial rotational velocity. So in my case, I might be talking about a star that's 10 times the size of the sun, with the composition of 75% hydrogen, 25% helium, that of the Big Bang, and say a rotational velocity that's like 300 kilometers per second. That would be a kind of typical rotational velocity for one of these stars. So with the first time step then, We would have our chemical composition and an energy generation rate, how much energy that star would be producing. We'd go through one time step for the nuclear reactions. So during most of its life, it will be burning hydrogen. So this would be the nuclear reaction chain for the proton-proton chain reaction, which fuses hydrogen and creates helium. And then once we've done that, so say we're burning hydrogen now, we have a new composition. So that new composition would now be a little less hydrogen and a little more helium and a new energy generation rate. And those in turn then are going to change lots of properties in the star, for instance, the density, the opacity, which is basically just how the light is absorbed throughout the star. You don't have to worry too much about that. The temperature gradients, how the temperature is changing through the star. And we end up with a new structure with a new luminosity, so that's how bright the star is, and a new radius and a new temperature. So we just repeat that for the star's full lifetime, and then that's basically how we watch these stars evolve. We watch how their brightness, their temperature, and other properties change over time, and that helps us to understand how these stars would live in reality. So what have we found? Well, I'm going to break the results down into 3 sections. So firstly, observable properties. So we use the Hertzsprung-Russell diagram in astrophysics to study the observable properties of stars. And in this case, when I say observable properties, I'm going to be talking about the brightness of the star, which we also call the luminosity, and the surface temperature. So one thing to be careful of with the Hertzsprung-Russell diagram is that the surface temperature increases to the left. Don't blame me, I didn't invent it. So this diagram, though, is very useful because it's useful for both observers and for theorists like me, because it allows us to both categorize stars. If we were to look out into space and take the surface properties of all of the stars that we could see, we'd find that they are naturally or sort of easily categorized in this way, where the less massive stars are cooler and less bright, and the more massive stars are hotter and brighter. And when they're on their main sequence, which is the main phase of their life where they're burning hydrogen, they're along this diagonal here. And then in later phases like giants or supergiants, or even ending their lives as white dwarfs, you would see them in these other regions. So it's very useful for categorizing stars in this way, but it's also very useful for studying how the stars evolve. And that's where most of my work would focus on. So I'm just going to give a HR diagram here, a blank HR diagram with surface temperature increasing to the left and brightness increasing upwards this way. And we're going to take a few examples of changes that might happen to a star in its life and see how that impacts the brightness or the surface temperature. So say, first of all, we have more nuclear fusion in the core. So now we'd be producing more energy, so the star is going to get brighter. Say then the star was experiencing mass loss. When the star experiences mass loss, it's going to reveal hotter layers underneath it, because the way the temperature profile looks in a star is that it's hottest at the core and then it gets cooler and cooler out to the surface. So as you lose mass from the surface temperature is going to get hotter. So that's what we would see typically for when the star is experiencing mass loss. Conversely then, if it's gaining mass, it's going to get cooler. And then if we want to take an example of something that might combine these effects, we could look at what happens when you have higher rotation. So there's lots of different things that could happen depending on the structure of the star, but a typical example of what happens when you have higher rotation would be that, first of all, you're able to mix more material into the core. So now you're going to have more nuclear fusion, so you're going to get brighter, but you also might have more mass loss. Because if the star is spinning particularly fast, so you might see the star evolve to the diagonal here. So that's an idea of how we can study these stars on the HR diagram. I want to give an example now of some of our models. So this is a brand new grid of models of the first stars that we've produced. And here are some of the massive models. So that's from 9 times the size of the sun up to 120 times the size of the sun. And I've indicated some key stages here, what we call the ZAMS, which is the zero age main sequence. That's just the start of hydrogen burning, right up until the end of helium burning. So this would cover most of these stars' lives. So this is how we would expect them to evolve along the HR diagram. So I just want to point out a couple of key features here so that you can get an idea of how this diagram helps us to understand the evolution of these stars. So firstly, this is a unique feature to the first stars. We have this hook feature at the start of hydrogen burning. So what's actually happening here is that because these stars form with only hydrogen and helium and they have no heavier elements, then they have to burn hydrogen through the proton-proton chain reactions, which I showed earlier. But actually there's another way, and there's another reaction for hydrogen burning, which is much more efficient. And so massive stars rely on this other reaction. It's called the CNO cycle. So the CNO cycle is different to the PP chain reactions because it needs carbon and oxygen to act as a catalyst for that reaction. And because the CNO cycle produces more energy, massive stars need it because they have much more, they have a much stronger gravitational pull. So in order for them not to collapse, they need to be producing lots of energy, so they need this CNO cycle. So the CNO cycle is needed for hydrogen burning, but as I said, these stars don't have it, and so they can't produce enough energy, and so they end up contracting. So that contraction is why you see these stars evolving to the left here, and because they're getting hotter as the star contracts. But once the core reaches a certain temperature, so the temperature increases, and once it reaches a high enough temperature, which was 100 million degrees, you can now fuse just a little bit of helium, just enough to produce some carbon, nitrogen, oxygen, and that's what will provide the catalyst for the CNO cycle. And now you can continue hydrogen burning as normal. So that's what happens here as they evolve then to the right. And you'll see that this hook gets smaller as you go to higher initial masses. And in fact, you don't see this feature at all for masses greater than 30 solar masses. And that's because the more massive models have hotter cores. So they can start this little bit of helium burning much quicker. In fact, for the more massive models, they immediately can do so, and then they can continue hydrogen burning through the CNO cycle. So that's one key feature. Another key feature is the smooth transition to helium burning. So I mentioned this at the beginning as well about in order to get to start helium burning, the core needs to be very hot. And so for stars more like our sun, the core would need to contract a lot in order to reach those temperatures. But as we've just discussed, these stars had to be hot enough to produce helium at the very beginning of their life. So they're ready to start burning helium as soon as they run out of hydrogen. So that's another very different feature of these stars. So yeah, the core is already hot enough for helium burning, so there's no contraction needed. So there's a lot that's happening in just this one plot. There's a lot that we can learn from the HR diagram, and there's a lot more that I could discuss. But let's move on now to what happens when we include rotation. So we'll take the example of the star that's 120 times the size of the sun, and this is our rotating model. So what happens with this star is that it actually reaches critical rotation halfway through hydrogen burning. So what I mean by critical rotation is that the star is spinning so fast now that it's actually nearly about to break apart. The outer layers have become unbound. So these stars can do this quite easily, as it turns out, because as I said, they're very compact and they don't have any mass loss. So all this mass is building at the edges, and it just makes it really easy for them to spin up and up and up. And so halfway through the hydrogen burning phase, our most massive model here, the 120 times the size of the sun, reaches critical rotation. So then we experience mass loss because, as I said, the outer layers have become unbound. And that's why the star will start evolving to the left here to higher temperatures on the HR diagram. But in fact, this mass loss actually then helps the star to spin down. So now it's going to spin slower. And eventually there's going to be no more mass loss because now the outer layers are no longer unbound. But what we found is that even after this event, when you've lost quite a lot of mass, the star can still spin up again. And so you can have these multiple mass loss events. And so in this case, just over the course of the hydrogen burning phase, this star has lost 3 times the size of the sun. And now all of that material will be orbiting around the star. And this is really important for us to be aware of, because then what's going to happen is when the star explodes at the end of its life, all of its all of the ejected material is going to crash in to that loose material that's orbiting around the star. And all the energy that's produced by that crash creates a really bright supernova. So when the James Webb goes up and sees really bright explosions, it's useful for us to question, well, is this from a really, really massive star, or is it from a slightly less massive star that just lost a lot of mass during its lifetime? So it's important for us to understand that. So moving on now to the chemical enrichment of these stars and the work that we've been doing there. Firstly, I just want to explain what I mean by chemical enrichment. So that's just the production of heavier elements. So how much carbon, oxygen, nitrogen, even iron that these stars might produce. So this schematic here is just to give you an idea of what these stars will look like during the helium burning phase, during the second phase of the star's life. So now you have the helium core where you have helium burning reactions. And while during the hydrogen burning phase, there was no reactions going on in the envelope, now we have a hydrogen burning shell. So we now have 2 burning regions in the star. So what happens here is that rotational mixing brings helium burning products to the shell, so to the hydrogen shell. So if you imagine that you had a bowl of water and you put a little piece of paper into the middle of that bowl and then you spun it really fast, the paper is actually going to move out to the edge of the bowl. So that's essentially what happens here, is that material from the core, as the star is spinning very quickly, can be mixed out towards that hydrogen shell. So in the core, during helium burning, there's a lot of carbon and oxygen being produced. And as I said, that can then be mixed out because the star is spinning so quickly, and it can be mixed out towards the hydrogen burning shell. When it reaches the hydrogen burning shell, you get this boost in energy production in the shell. And now you can start producing nitrogen as well, because what's happened here is you've triggered the CNO cycle. So you remember I was talking about that for the hydrogen burning phase, when you're burning hydrogen in the core in order to sustain the star against all of its gravity, you need to have the CNO cycle. So that kind of boosted the energy production of the core. In the same way here, the hydrogen shell starts at the beginning of helium burning only using the proton-proton chain reactions to burn material because it doesn't have carbon and oxygen. So once it gets carbon and oxygen that's been mixed out from the core, it creates this boost in energy. And now we can produce nitrogen. So because of this, it's expected that rotational mixing would increase the amount of nitrogen produced, because it's thought that nitrogen will then be a tracer for how much carbon and oxygen could have been mixed out from the core, which would tell us about how fast the star was spinning. But actually we found that it's not that straightforward. So this plot here is showing the nitrogen abundance So the amount of nitrogen that's been produced for different initial masses of stars, where the black diamonds represent the models without rotation and the red diamonds represent rotating models. So don't worry too much about the legend here. This is just showing the initial rotational velocity that we choose, which is 40% of the critical velocity. But in any case, as I said, what we expected to see here was all of the red diamonds would be larger than the black ones, but that's not what we found. We do see that in the case of the less massive models, so for the 9, 12 and 15 solar mass models, we do see a large increase in nitrogen compared to the non-rotating models. But what happens after that? Well, what we found is that more massive rotators actually experience an earlier triggering of the CNO cycle, which in fact hinders enrichment. So let's come back to that picture that we had of what's happening during helium burning. So when the carbon and oxygen reaches the hydrogen shell and you get that boost, if that boost in energy is strong enough, then it can in fact suppress the size of the core. So this is just to show you what it was like beforehand and what it's like now. And in fact, now that the core is suppressed, that's actually going to make it even more difficult for carbon and oxygen to be mixed out and to reach the hydrogen shell. So now you've sort of limited yourself to whatever carbon and oxygen you had at the start of the helium burning phase. And so you've limited how much nitrogen you can produce. That's not the only interesting thing about this plot though, because what you might notice is there's a lot of variations in the amount of nitrogen produced. And that's actually because there's another way that you can produce it, which is after helium burning in what we call hydrogen-helium shell interactions. So just in the way that during helium burning you have a hydrogen shell, during later burning phases, like carbon fusion or oxygen fusion, then you would have both a hydrogen shell and a helium shell. And if these two are close enough to each other that they can interact, then they can produce an awful lot of nitrogen very quickly. And this is basically because all you need for nitrogen production is helium burning products in a hydrogen burning region. And so at late phases, depending on the structure of the star, this can quite easily happen. So what this tells us is that we can't rely on just nitrogen as a tracer for how fast these stars are spinning. We actually need to understand the stellar structure very well in order to predict that accurately. So lastly, I'm just going to talk a bit about ionizing photons. So don't be too freaked out by that. I'll break it down. So what is a photon? Well, really to ask what is a photon, we have to ask what is light. So light is interesting because it behaves as a particle and as a wave. And the particle that we're talking about there, this massless particle, is a photon. So when you hear about photons, really that's just little packets of light. But what's an ionizing photon then? Well, that's just photons with lots of energy, so very energetic light. So if we look at the electromagnetic spectrum here quickly, then this is going from radio waves to gamma rays in decreasing wavelengths here. The scale here is wavelength in meters. And if we want to talk about the most energetic light, the ionizing photons, that's this region of the electromagnetic spectrum. And actually massive stars are very good for producing lots of ionizing photons. Why are they important? Well, they're important for reionization. So when I mentioned at the beginning about, at the beginning of the universe, all of the material was ionized, and then we had the dark ages when things cooled down and you could have neutral hydrogen. But then when the first stars came along, then we were able to reionize that hydrogen. And there's a lot of people who are interested in reionization because it's a key It's a key era or a key epoch in the history of the universe. And it's thought that the first stars are mainly responsible for that. So we want to understand how much could these stars have contributed to reionization during their lifetimes. And we can do that by predicting the ionizing photons produced from our models. So what have we found? So ionizing photons come in three main species, three main flavors. So first of all, we have hydrogen photons. So these stars will produce lots of hydrogen photons. The more massive stars are going to produce more photons per second, but they also live for shorter times. I'll say more about that in a second. The next species of photons is the helium-1 photons, and those are just more energetic, essentially, than the hydrogen photons. And then the most energetic case that we're interested in are the helium-2 photons. And so, as I said, the higher mass models will be these ones that produce that have the highest ionizing photon production rate. So that means they produce the most ionizing photons per second. So there's lots and lots of this very energetic light coming from these stars every second. But they also live, they don't live as long as less massive stars. So the most massive star that we're including here, the 120 solar mass star, that only lives for about 3 million years. But 9 solar mass star, 9 times the size of the sun, would live for roughly 30 million years. So it has a lot longer to be producing these ionizing photons, but it's producing much less per second. So yeah, so they also have much shorter lifetimes. So we're interested in understanding what mass produces the most photons in its lifetime, because that's going to tell us what ones to focus on. So when we have observations and we know, say, how many 50 solar mass stars there are and how many 10 solar mass stars there are, then we can tell how many ionizing photons they would have produced by this work. And what we've found is that the total photons produced increases with initial mass. So even though these most massive stars have much shorter lifetimes, because they have such high ionizing photon production rates, and that's because they're so much brighter and they're so much hotter, and that means that they produce more photons over their lifetime. So if we want so if the first stars were to contribute a lot to reionization, and that means that there must have been a lot of very massive stars among them. We also plot here the star symbols show the models with rotation. So it might seem like they're not very different to the non-rotating case, but you have to remember that this is logarithmically scaled. So this is going from 10 to the 61 to 10 to the 62. So these actually really big changes. And in fact, we found that these ionizing photons are affected by up to 25% by whether rotation is included or not. So they are more affected by initial mass than rotation, but there's still up to a 25% change with rotation. So it's important for us to understand whether these stars, well, we expect them to be spinning very fast, but we want to understand how much that will impact the ionizing photons produced. So I'll just conclude there and I'll say a few last points before I open up to questions. So the first stars are crucial to understanding the early universe and how subsequent stars formed. And through stellar evolution modeling, we can understand how they evolved, including the nature of their rotation, their mass loss, the amount of heavy elements they produced, and their contribution to reionization. And stellar evolution can also then be used to predict the final fates of these stars, including their explosions, the effect that they had on their environment, and even it can be used to predict the observations, so what we'll see with the James Webb. So thank you, and I'll take any questions now.
Thank you very much, Laura. If people have questions, they can ask them in the chat section. I should have mentioned that earlier. Or you can turn on your microphone if you want to ask a question verbally. So I saw one question there came in chat from Laura Quigley. Let me read out his exact question rather than try to remember it from memory. Oh, I've lost my chat box. I did do too much on this computer at once. There we are. I lost it. Oh, there. Yeah, so Laura asked, what is the age of the oldest stars in the Milky Way?
The oldest stars in the Milky Way. I'm not actually sure of what the metallicity is, what the lowest observed metallicity is in the universe, which would tell you more about how old they are, because if stars formed with less metals, then that tells us that they formed at an earlier stage in the universe. So I'm probably not the best person to ask this question, but I would guess, I mean, there's definitely stars that are billions of years old, and I would imagine you'd be going back to I mean, all of the galaxies really can be traced back to the first stellar population. So I would imagine if you were able to find one, you'd probably find stars that are roughly 10 billion years old in our own galaxy, if not older. But the trouble is that these can often be much more difficult to detect, because if a star is that old, is 10 billion years or older, then what that means is that it's very low in mass, or well, it would be roughly 80% the mass of our sun, or maybe even lower, and that means that they would be quite faint, so they'd be more difficult to see. But yeah, I'm not sure of the most recent observations on that.
Okay, well, we have another question here from Tortorma, I believe is the pronunciation. Why do stars rotate?
Oh, that's a good question. Why do stars rotate? Well, it's not that they rotate because they need to necessarily, but it's just because of how energetic the environment is where they form. So stars form in what we call nebulae, and in the modern universe, a nebula would essentially be the remnants of an old supernova. But in the early universe, it was just a cluster of very hot and energetic gas. And so all of this gas essentially clumps together, and it's very hot and it's spinning around itself a lot just because of how much energy it has. And how much that gas cloud is rotating as it's forming stars is what determines how fast the stars will rotate once they're formed. So if we want to understand the rotational velocities of stars while they're alive, then we need to understand the environment in which they formed.
Great. Another question from Morgan Flynn in County Waterford, who asks, how common were these stars in the early universe?
How common were these stars?
Does that mean how many of them were there?
I'm not sure. Maybe, yeah, the kind of density of stars in the early universe. It's a good question, and I suppose to answer that you'd have to know two things. You'd have to know how much matter there was in the early universe, and you'd have to know how efficient the early universe was at turning that matter into stars. I suppose my quick answer would be a lot less than there are today, but also there would be much more massive stars as well. Yeah, that's a question that will probably be answered a bit better by when we have the James Webb observations, because that will tell us what these earliest clusters of stars looked like. And that might help us to understand how many, not just how many stars, but also how many stellar populations there typically were in the early universe. But I would expect that there was a lot more, even more empty space in the early universe than we would see today.
So watch this space is the answer.
Yeah.
And Annika in County Kildare says, this might be more of a cosmology question. I wonder how far back do we think the theoretical limit of looking back is? Am I correct in thinking if the expansion was slowest at the start, we couldn't look back past a certain point since we couldn't have outrun that early light?
That's a very good question. The main thing that limits us into how far back we can see is the cosmic microwave background. Because what that is it's the sort of last stage of when the universe was fully ionized. And when the universe was fully ionized after the Big Bang, people often refer to it as like a hot, dense soup of particles. And it was very dense. And what that means is that it was very difficult for light to travel through and escape from it. And so when we look very far away, what we're seeing is the last place that light was able to scatter off of. So if we look at the sun, then what we're seeing is the the photon that came from the sun. But when we look at the moon, we're looking at a particle that's bounced off of the moon, having come from the sun. So we need to have plenty of space for that photon to get through in order to reach us. So, I mean, it's already difficult enough to see the early universe in that sense, because there's plenty of it that would be blocked by other objects between us and that distance away. But once you hit the cosmic microwave background, that essentially just totally limits us there, because light is there's too much scattering happening within there. That's one thing that's really special about this new era and this new method that we have of observing through gravitational wave detections, because now we don't have to rely on where light was last scattered from. Gravitational waves don't care really what's been in the way, and they'll get to us. So that's one way that we can see back now. Yeah, in terms of how, if we could see back further, if there was slower expansion, that is more of a question for a cosmologist, unfortunately. But it is a very good question, and I'm sure you could find some cosmologists online and ask them that. But yeah, the main challenge for us is the cosmic microwave background.
Great. I got see 4 of the questions here, 2 short ones, 2 long ones. I'll read out the first short one. Is there, John Carroll asks, is there a dominant plane of rotation, both stars and galaxies, across the whole universe, or even clockwise versus anti-clockwise?
I don't think so, not to my knowledge, but I'm not sure, to be honest.
Well, shall we move on to the next question? Leave that for one of the cosmologists. We will have more cosmology talks during the year. We had some very good ones. Andy Briggs jumps to mind. He explained that first black hole picture brilliantly, if you want to go back and look up his lecture on the DVD site. But anyway, yeah. Yasya from County Dublin asks, you mentioned that there is an element that can be found in our structure that came from a supernova explosion. What was that element, and are there more elements we know of?
So I think what I was referring to there was all of the carbon that's in your body. We expect most of that to have come from a supernova. But that's true for pretty much anything in your body, like even like the oxygen that you breathe and stuff, it's not just in your body, but all of the material that we have on Earth has likely come from a supernova, and it's likely that's the supernova that our sun formed from, and all the other planets as well. So I suppose I just use that as an example because I think it's interesting to point out how important supernovae and explosive events like them how important they were for providing all of these elements that we take for granted.
Yeah, I like the way a lot of people say rather romantically or poetically that we're all made of star stuff.
Yeah.
But there is a less romantic way of saying it, which is that we're all made of nuclear waste.
Exactly, yeah. Dramatic depths.
I can't remember who said that one. We have another question here from Gregory, age 8. Nice, simple one. How big can a supernova be?
How big can a supernova be? Wow. I mean, in terms of energy and brightness, I mean, they're so big that they can be like hundreds of times, thousands of times brighter than a star would be. So they can be really dramatic events. In terms of the size of them, so if you look at the Crab Nebula that I gave as an example earlier, which is the remnant of a supernova, that's thousands of light years across. So the diameter of it is thousands of light years. So they're really, really big. They just take up massive amounts of space. So that's why it can be so easy for us to see those nebulae, and we get lots of fabulous pictures of the Crab Nebula, etc., because and they look nice and colourful with all of the hot, dense material in them. But yeah, they're very massive, thousands of light years across is a kind of typical size of the remnant of a supernova explosion.
Was that somebody there wanted to ask a question verbally? Trying to come in there? I might have clicked the wrong button. We don't hear from you in a few seconds. I'll read out the next. We've got a few more questions. Some of them are cosmology. We might just skip those ones. I don't know if you know the answer to this one, Laura. It's from John Carroll again. County Armagh. If the James Webb Telescope malfunctions, will it be accessible to astronauts the same way Hubble was?
I'm not sure. I'm trying to think exactly where they're putting it in space, but I would imagine so. I don't think it's going much further away than Hubble was. So yeah, I think they should be able to access it. And I hope they are, because if anything does go wrong, we want to make sure that we're still able to fix that and to get observations back to us. Yeah,
there are lots of great comments coming in about the talk. You can read them on chat later on if you wish.
Thanks, everyone.
So one last question there. Oh yes, yeah. So this one's more to the point of subject of the talk. And by the way, if you have questions like the one about James Webb Space Telescope, I don't think they have plans to service it, but there are apparently some things been added to it that maybe future missions could be developed. But send that into as a letter to the editor of our magazine. We'll get one of our space correspondents to answer that one. The next question just scrolled off the top of my screen. Let me bring it back. It's not the question I was looking for, but this is a nice, easy one from Danny in Cork, age 12. Has any planet we know of been swallowed by a black hole?
Not one that we know of. But I would say that has almost definitely happened, because if there was, so if a star collapsed to a black hole that had planets around it, which is likely to have been the case, then I think those pretty easily would have been swallowed into the black hole, or at least would now be in the accretion disk of that black hole, and be sort of feeding it now.
Okay, and one last question then from Sean Farrell in Dublin. He asks, did those early stars disintegrate to form the galaxies existing today?
So good question. Yeah, they didn't disintegrate to form the galaxies, but the galaxies started off as what we just call clusters of stars. So when the first stars formed, they formed in these clusters. And then as the more massive ones died and produced supernovae, and more stars formed, and the sort of dense material in the universe started to clump together more and take shape, that's when the first galaxies started to take shape. And so by understanding how many massive stars there were and the nature of their explosions, then we can figure out more about how those first galaxies were shaped. Really those galaxies have been consistent then since then, because the stars form in a region where a previous star has died. So yeah, if we can understand what the very early universe looks like, then really that's just the only change, or the only significant change between then and now, is just that the galaxies, because the universe is expanding, the galaxies are moving further away from each other.
Great. And the last question we'll take from Sean Farrell in Dublin. No, I've already asked that one, haven't I? I have one last question. Maybe I just missed it. An awful lot of thanks coming in, which is great.
Thanks.
Pushing the questions down the screen faster than I can scroll. So we can leave the Q&A there for the time being. If you have more questions, you can always write into Astronomy Ireland. We're going to tell you briefly about what's to see in the sky, how this month is terrible for astronomers, and how it's still winter, not spring, as a lot of people would have you believe. So I'd like to thank Laura for giving me a fantastic talk again. It's going to be really remarkable to see what we find out about these early stars in the universe when James Webb comes on view. And it's nice to know we have an expert in Ireland who can tell us all about it. So thank you very much, Laura, on this International Women's Day.
Thank you. Thanks so much for having me, and thanks for everyone who came and listened, and thank you for asking questions as well. Happy International Women's Day.
Well, let me just briefly close the meeting by telling you, actually I should put my video back on. That button there, I think. Need to maximize the screen. There we go. Oops. Let me tell you brief about what's happening in the sky. All this, by the way, well, most of it is in the magazine, and a bit of it in April will be in the next magazine that'll go out at the end of March. A quick review of planets on view. Mars and Uranus are the two answers. The rest of them are all too close to the sun. Mars, you can see with the naked eye. Uranus is going to be it's going to be near the moon again, and it's a fantastic sight. Not that it's spectacular, but very few people in the world have ever seen it live. It is technically just barely visible to the naked eye, but none of the pre-telescope astronomers ever saw it and realized it was a planet. So we have to wait for the invention of a telescope to see it, and you can do something similar in a few days. I'll tell you about that in a moment. We're just going back to Mars, first of all. We were featuring in the magazine that it passed closest to the lovely Pleiades or Seven Sister Star cluster earlier last week, but it's still fairly close. And in fact, it's passing between the Hyades V-shaped star cluster and the Pleiades for the next week. So that's a view just to behold with the naked eye. Mars is one of the brightest stars in the sky, and it's about the same brightness as the brightest star in Taurus, Aldebaran, just to its left. Hard to tell which one is brightest. The two of them are actually slightly orangey red in color, so they're like twins at the moment. So do check that out. And if you've got a camera, you can take fantastic pictures of both clusters with Mars in between them over the next few nights. Hopefully we'll get a few clear nights between now and about a week or two's time, when Mars is going to move quite a distance away from them. That's Mars, the best planet to view. Not great in the telescope. It's very far away, so its disk is quite small. Focus on the pictures coming back from the surface, but from the spacecraft, instead of hoping to see any great detail on the planet yourself. It'll be great in 2022 when it's close to us again. So what else is happening? Well, we mentioned, and this links nicely into our next talk, which I'm going to tell you about in a moment, the International Space Station in morning skies. I saw somebody in chat asking for the time again. Remember, it's on our Facebook and Twitter feeds. And the answer is 5:32 a.m. for the Starlink train. That's about 60 of them very close together. And 2 minutes later, in fact, the train will still be going across the sky when the International Space Station blazes over. Now, it's much bigger and much brighter, but it's only one object moving across the sky. So 5:32 a.m. and 5:30, 4 a.m. I've got my alarm set for 5:20. Just have a look out, see if the sky clear. If it is, give me a chance to get dressed and go outside. So that's something special to see. We're spending 100 billion euros on the ISS, and the 7 people on board at the moment, including some women on International Women's Day. And I'll tell you more about how that links into our lecture in just a minute. The other thing that's happening, I mentioned Uranus is close. We'll go through the rest chronologically very quickly. This is all in the magazine, as I said. On Tuesday next week, the 16th of March, that's the day before St. Patrick's Day, Uranus is close to the moon. They'll be in the same binocular field of view. We have a diagram in the magazine showing what that looks like. The moon's a lovely thin crescent, so it won't be particularly bright. So you'll be able to see the Earth shine on the moon. That's the dark side of the moon lit up faintly by sunlight reflected off the Earth. The lovely crescent in your field of view, and then Uranus above that, also in your field of view, as just a little star-like object. So don't miss that. It's very rare for anyone to ever see Uranus live. So enjoy that. It's a unique chance because the moon is such a thin crescent, it won't swamp the dim light of Uranus. I mentioned then starting Thursday week that the International Space Station is in evening sky, so it'll do that. It'll fly over every night in the evenings, so you won't have to get up 5:30 in the morning, from the 18th of March to the 3rd of April. So enjoy that. There'll be predictions daily on the Facebook and Twitter. And that night, in fact, Thursday, 18th of March, and the next night, the Friday, Mars is going to be near the moon. And the moon, because Mars is near the Pleiades, will be near the Pleiades and the Hyades. So it's a very busy sky. And it's a fairly thin crescent moon. So it won't swamp all the faint stars. So even on the Friday night, the moon's only about a third of its diameter Sunday. So it looked like a fairly thick crescent. There are diagrams, all this in the magazine. Just remember, next Thursday and Friday, not this week, next week, there's going to be a fantastic naked eye sight with Moon, Mars, and those clusters. And then, this is the bit I've told you people have been misinforming you. We're in winter at the moment. Don't believe anybody who tells you the spring begins on the 1st of February, the so-called Celtic spring. The rest of the world doesn't obey that rule. And don't believe the Met Office that spring begins on the 1st of March. It doesn't. The seasons on the Earth are all defined by the tilt of our axis, and we have equinoxes and solstices, and they define the seasons. They always have. The rest of the world over, you'll see the definitions are strictly this. They don't have these, it's the warmer month, daffodils are coming out, etc., etc. Yeah, daffodils come out in winter, the end of winter, not spring. So the equinox this year is on the 20th of March at 9:37 a.m., actually, officially Saturday morning, 20th of March, and that's when spring begins. And it lasts until the summer solstice in June. And when we go and colonize Mars and other planets, they've got a tilt as well, and their seasons are going to be based on the equinox and solstice. So there's no sense getting it wrong now. I've often said this to people in media, that the seasons have always been clearly defined, and let's stick to the strict definition. So enough of that. I'll get down off my soapbox now and tell you that that night as well, that Mars is closest to the star Aldebaran. Now, they're only 7 degrees apart, which means you'll barely fit 2 into your binocular field of view, but that's technically when they're closest. After that, it begins to move away. And then the real tragedy of the month is that on the last Sunday of March, the 28th, at 1 a.m., summertime begins. So the clocks go forward an hour. And that means that sunset comes much later in the evening, and you have to stay up very late to get a dark sky. What a terrible time for astronomers. That's going to happen at the end of this particular month. So when we come back to you in April, in our next lecture, it'll probably be bright outside when we start. Terrible time of year. I much prefer the winter when it's dark for as long as possible. And that night, curiously enough, is also the night of a full moon. And this is interesting because, first of all, the name of it is the worm moon, because earthworms apparently come out this time of year. But it's also the first of 4 supermoons this year. Now, a supermoon is when there's a full moon at the time when the moon is slightly closer to us in its egg-shaped orbit than at other times. So there's going to be 4 consecutive supermoons. First is on 28th of March. You'll see details of that in the magazine. I'm sure it'll be in the media. It's supposed to look up to 30% brighter than when it's at its most distant and a full moon. You probably don't really notice that, but people will go out looking for it. Full moons are very bright, and they'll be convinced that it's brighter than normal. It's all a bit of fun and gets people looking up So I'm more in favor of it. So as I said, all this in the magazine. Do enjoy all those sites, and do write into us, email into us if you see anything, magazine@astronomy.ie, so we can publish your reports, especially Irish reports. And just to end on events, but they start again October 12th, and you can enroll for now if you go to astronomy.ie/class, or just go to the events page, scroll down, October, you'll see it there as well. The next lecture is quite an interesting one. I said that we're spending 100 billion euros on the International Space Station, and people often wonder, why are we spending so much money in space? 100 billion on the space station, 10 billion on James Webb Space Telescope, 3 billion on a Mars lander, and the list goes on. Well, there are lots of feedback for the human race, and you'll see different space agencies saying how many extra dollars they get for each dollar that they invest in the space business. It's a long story. Basically, we can justify it all financially. But one thing they do on the International Space Station is they do quite a few commercial experiments, some of which are to test out new drugs. I remember in the early days of interferon, which was hoped to be a cure for cancer. Turns out it helps with some, but it isn't the cure we wanted. But you could produce these drugs on the International Space Station in small quantities for trials, much, much cheaper than building a plant on the Earth that had to do it in gravity. And then you could do the trials and see, was it the cure-all we hoped for, and build massive factories on the Earth then to commercially produce it. So the Space Laboratory, ISS, has great uses. And our next speaker is an expert in that particular field, Dr. Martin Braddock. He's going to talk about the best of all worlds, space, drug discovery, and drug development. So if you want to know how we justify all these billions, do tune in to our April lecture. It's on the 12th of April, so usually on the second Monday of the month, 7 p.m. You can get tickets for it on the website astronomy.ie. Just go to the events page, scroll down to the 12th of April, and book your tickets there. Tell all your friends to come along. That's all the announcements we have. Don't forget to follow us on Facebook and Twitter, because not only we do satellite, we'll post them on there as well. We had a few scares in the last week, and the weather worked against us, and a few of them didn't materialize as strong as we hoped, or happened over the US instead of over Europe. But we'll keep you posted whenever we see anything coming along. So last thing to do is, if you're not already getting the magazine, please do order the magazine, support Astronomy Ireland. You can't miss it when you go to astronomy.ie. We'll see you all back here, hope, on April 12th. And just a very big thank you to all of our volunteers who helped make the talk run smoothly this evening. And of course, a very special thank you to Laura Murphy for her brilliant talk on the first stars in the universe. Thanks for joining us. We'll see you next month. Good night.
Thanks, David. Good night.
Let's end the recording, shall we? Okay, ladies and gentlemen, if you're free to sign off, let's see, we've still got 13 people hanging on, probably some of our committee.